So, hello and welcome to the KISSsys web demo, where today the focus will be on the new features in KISSsys 2018. We are broadcasting at the moment live from BubiCon. My name is Cengiz Yilmaz, and I will show you today the following topics. Like first will be the displacement for bevel gears based on shaft bending. Then our new interface to the Gleason GEMS software, where we can have the exchange of gear data. GEMS, maybe you know already this, which is a calculation software for gear stages, where you can analyze single stages, and there we can have some exchange of gear data and results. Then topic number three will be calculation of eigenfrequencies and vibration modes in shaft systems. Then we will have a look to system reliability calculation, how the handling is and how we can interpret the results there. Last point is will be we will show some handling improvements, like how to handle power split kinematics new in KISSsys. Then some improvements in the settings table, and maybe most of you didn't know that it's possible to create 2D plots in KISSsys. It was already possible, but we improved this functionality as well. So this will be one of the last points. Yeah, you have in general, you have the possibility to write questions in the question window of your webinar tool, and my colleague Michael Stangl will answer them live during the demo. And we will handle a couple of questions at the end of the demo and read them aloud for all, that everybody can make the profit of the questions. So now I would like to start with the first point, displacement for bevel gears based on shaft bending. If I go to KISSsys now, let's open the single bevel stage model in KISSsys. And here you can see that we have, if I go to boundary 1, this is the input boundary where we have the pinion shaft. I have here a speed of 1000 RPM and a torque of 50 Newton meters. So in total, I give a power of 5.236 kilowatt to this gearbox, to the pinion shaft. And now I would like to calculate the displacement which are resulting from the bending of the shaft, just from the bending of the shafts. To do that, we have a new template under the standard templates in KISSsys. You can find it here. It's a new icon, which we can just load in to our model tree. The first window appears to select the stage which you want to consider. Since we have just one bevel stage, we can select single bevel stage from the list. And the selection here can be closed. And then you will see an interface like this. In the first part, in a header, here you can do some graphical, you can set the graphical settings here. This means draw the deflection lines. If I say yes, this will create the deflections in the actual 3D viewer. Then you can scale these deflections with a scaling factor, which you can set here. And there is the type for the values. You can have either the Gleason standard EPG values or the Klingelberg VHJ values. And according to your selection, we convert these values below. So let's switch back to Gleason EPG. And again, if you did wrong selection in the beginning, you can do this. You can select the stage again here. We've set up Modul. And with the calculation, you can run the displacement calculation now. It's not changing because I already did it before. So what we can see in general is we have for the different shafts in X, Y, and Z directions, the displacements for the pinion shaft and for the wheel shaft, and also the tilting around the X, Y, and Z axis. Yeah. And these values are automatically converted to the EPG values according to the conventions with the sign. And these values are ready now to transfer to GEMS, for example. Now, just a short, maybe again, additional information. What does it mean if we take these X, Y, Z values? From where do we take them? If I go to one of these shafts, let's say to the pinion shaft, here it's already written that it's the results at the middle of the phase width. So if I, just to make it clear, if I open the shaft calculation, we have the middle of the phase width of this bevel gear, and in the center of the shaft, we check the displacement of this point in X, Y, and Z direction, and also the tilting at this point around the X, Y, and Z axis. Okay, then if you check the 3D view, since we activated here the deflection lines, you can see with the scaling factor how it would deflect. We can see clearly the pinion shaft deflection and also a bit the bending of the wheel shaft. Let me show it in the new 3D viewer as well here, which is a bit easier to handle. So in the properties of it, I can activate, for example, the radial displacements. So you can really see here this shaft, and also if we have some axial displacement, you can see how the shaft moves axially as well. Maybe 1,000 times. So this creates really big. Yeah, we can see the bending here clearly. Yeah. Okay, that's regarding these bevel displacements. For sure, if you would change temperatures of the housing now, you would see the effects as well here in these displacement values. So, as I mentioned before, these displacements are needed if you want to do the contact analysis maybe in GEMS for a bevel stage. And now I come to the second topic with this introduction, which is the interface to the Gleason software GEMS. In GEMS, I already started here the calculation software from Gleason, and if I open the sample job here, which can be the hypoid stage, for example, yeah. Then you will see from that hypoid stage the geometry values, and I exported already a predefined file here from GEMS, which I would like to import to KISSsys. So to do the import, first of all, you need to add the template related to this for this interface. You can find it on the standard templates here. GEMS template interface GEMS. Close it. And if I add it, you will see automatically the interface here of this template. So one comment here is that you need to have first the bevel displacement template in order to have the interface GEMS template working. If you don't have the bevel displacement template before add it, then it will automatically also create it together with the interface GEMS template. And first of all, we have to define the loads here in KISSsys. So that's the first thing you have to do. We have the two bins, for example, absolute values, hours, and the speed is defined at the pinion shaft, the torque as well. And let's say I would like to use vectors and fraction from the total lifetime. Okay. And I have two conditions. For speed, I say speed and torque. I use the same input conditions with vector, just multiply with vector 1. And here for the torque, I use the coast condition. That's why I would like to have the negative speed and negative torque. And for the drive condition, I have the positive values. So this is just to check what happens when different flanks are in contact and different flanks are driving from the pinion shaft. Okay, so these are our loads, drive and coast conditions. And the next thing would be the exported data from GEMS to import it to KISSsys. So I already have an exported example from GEMS. This is this one which I just exported from here from the design data exchange tool. I did an export from here already, which we could also do again. So this is this one actually. I already did the export. So you can also see how it looks in XML format, this example from GEMS. And now I have to import it to KISSsys. Maybe before I do that, just to visualize it in an easier way, I can show you a bit with the pictures how this communication works. So we have KISSsys on one side and GEMS on the other side. And there are many different possible points which we can follow. So either I have a bevel pair geometry here created in GEMS, or edit the values added in GEMS, and I would like to import. I can import it here to KISSsoft, and I have the loads defined in KISSsys. I have the system defined in KISSsys, and I can perform the system calculation there. And as I showed in the beginning, I get the displacements there, the bevel displacements, which I can extract again together with the geometry data to GEMS. And in GEMS, I can perform a contact analysis, for example, and check the meshing and also go forward to the manufacturing processes, or I can also import back the results from the contact analysis of GEMS in KISSsys to check how they look in the system tool. Yeah. So this is a bit to summarize this communication here between the two tools. And I would like to just show you now, we exported the geometry at the moment from GEMS, and I would like to import it to KISSsys and do the calculation and export it to GEMS then. So here I would like to import this data from GEMS. And this is, let's say, the exported file. And you can already see it can be that some settings in KISSsoft, they have to be changed accordingly, because now I'm importing a hypoid stage and my model was not ready for this stage, and it has to that some parameters have to be changed. So here it's the calculation method, and I just say okay, yes. And what's happening now is KISSsys is reading in this data, doing the calculation with the defined load cases, and exporting also automatically the load cases together to this file in an XML format, as you see here in the message. Maybe let's switch to English, is much easier to understand for you. So now we exported this data, and I can go to GEMS and import the loads again back. This is the same file which is overwritten from KISSsys together with the loads. And if I import this file, I can find back the loads here as well. And I can run here the contact analysis in GEMS. Yeah. So I can start the calculation, but this can take some time depending on the number of load cases. I have already a result file created, which I can already import to KISSsys. So it depends always on the geometry and on the cases. So maybe I would like to make the time shorter. I would like to import the results from an already calculated file, which is the same geometry, actually just calculated before. Yeah, and the import of the results, you can go to import results in KISSsys and check here the exported XML file, which is coming after the calculation in GEMS. And we have some graphics generated automatically, which you can check here with generate graphic. First of all, we can see the contact pressure either from pinion or from the wheel. And for the different load cases like drive or coast, what we defined here in our load cases table. So let's check the contact pressure on the pinion. So this is actually on the flank for drive condition of the pinion. Then if I check it for the wheel, it looks the following way. And it's again important to mention these loads which we had before can be a bit too less for this geometry. This is just to show you a bit how the communication works and what is possible for this interface. Yeah. And another point is we can show the sliding velocity in 2D, or maybe which is also something which is also interesting, the mesh stiffness or the transmission here, the transmission error here at the last point. Maybe we can make it bigger for the wheel for drive condition here over the mesh, and also for the same for the pinion for sure for drive condition. And let's check the coast condition. Yeah, looks slightly different. Yeah, so that's it actually. What we mean with the interface between KISSsys and the Gleason software GEMS. As you see, there are many possibilities. You can also just define the geometry in KISSsoft and export the loads, and then do the contact analysis again in GEMS. Or you can also do it in the way how we did it. You can import the load from GEMS to KISSsys and do the calculation by exporting the loads to GEMS and importing again the results. The motivation here was, for this example, is that's a hypoid stage. So the contact analysis, we cannot do the contact analysis of hypoid stage in KISSsoft, but with this interface, you are able to export it and do the contact analysis in GEMS and check the results again in KISSsys. So if you have any questions related to this topic now, you feel free to ask Mr. Stangl. He's sitting next to me and he's ready to answer your questions. You can just write in the questions field or chat field of the GoToWebinar tool. Okay, so Then I would like to switch to the third point, which is about the calculation of eigenfrequencies and vibration modes in shaft systems, where I would like to open one of the example models here, which will be a 4-speed transmission gearbox, so that we also have something for the automotive industry. Yeah, this will be a 4-speed gearbox where we have the second speed in, so we will see details in the model. And I would like to show you the model analysis of such a system. For sure, we have also 2 other points to show, which we could show, but these functionalities are in beta state. So I would like to show you just the model analysis, the force response, and the generation of Campbell diagram. These 2 points, they are in the beta state, so they will not be shown today. We already had before some 1 hour web demo about these topics from Mr. Zotos from KISSsoft AG again, and you can also check our YouTube channel to see the details about the eigenfrequency and vibration analysis of system. He did a quite deep explanation there during 1 hour. Yeah. So today is just that we show the model analysis, which is in our price list finally. So it costs something, and yeah. So that the goal here today is that you see the functionality, you see the handling of it, and why we put it to the price list is that we could do some checks with other MKS software, some additional calculations, and we could see that we get good results or reasonable results that we can really put it to our price list finally. Yeah. So here again we have the 4-speed transmission gearbox, where at the moment where we have, let's check the loads, maybe we have 47 kilowatts here, 3000 RPM, 150 Newton meters, and we are at the moment at gear number 2 is in, it's this stage, and I would like to perform now I would like to do the eigenfrequency calculation, the model analysis of such a system. So you have the option to either use the elements on the left hand side here, which are the calculation elements, and drag and drop to the root directory, or you can also go to the element box and check the calculation elements here, and we can find the KISSssoft shaft system here back. I will just click on the root directory and click on the specific element to add it to my Model 3. I close it, and now to calculate perform the model analysis, we can make a right mouse click on this element and here just use model analysis. Yeah, and I would like to do the calculation of the first 4 eigenfrequencies. Then regarding the meshing stiffnesses, you have the option to take it from the ISO calculation, or you have also the detailed option to use it from the contact analysis results, or you can say the meshing frequency, the meshing stiffness is infinite, or do not take into account the stiffnesses of the meshes. So let's use the ISO calculation as a reference, and I would like to also see the bending modes, the axial and the bending modes, not only the torsional vibrations. And gyroscopic effects, I would like to neglect at the moment. Okay. So then the software is starting the calculation. Depends on what you selected here. This can take some time. So if you would calculate just the torsional vibrations, then you would have it in a couple of seconds. This can take around half a minute now because of the coupled vibrations, because of the bending and the axial modes in addition. And yeah, what we can say here is that the model which we use in the background is we have the stiffness of the shafts, the inertia and the stiffness of the shafts. We have the stiffness for the bearings, and we have the gear inertia and the meshing stiffnesses of the gears. And all together is vibrating, and we are calculating the eigenfrequency of such a system. So calculation is finished. And the first thing what we can do is we can check it visually in this 3D viewer. And if I open the settings of this 3D viewer, I can show you the calculated results here. So the first is a gear body vibration. Then this is the first mode. Then second mode is we have 30.53 Hertz. And let's check what we have here. We can see that we have just the torsional vibrations here mostly. Even if I do the scaling, put it higher, so it's more torsional. Quite less bending here maybe, but in general it's more torsional vibrations. Then let's see the third eigenmode, eigenfrequency. So we have here the bending is stronger for these gears, and in general we have torsion and bending together. For the last one, similar but vibrating. For the bending mode is stronger here for this gear here. Okay, so this is something what you can analyze graphically or in 3D. And then what you also have is the amplitudes of these different modes. So we have for the different shafts, and eigenfrequencies, we have over the shaft the different amplitudes. So the displacements for in x, y, and z direction, and also the rotation around this axis. So you can plot them manually if you like. We have also some plots. We can also create the plots automatically here, but I would not like to start this plot generation at the moment, which takes also some time. So what I would like to show you is also as a report, the summary report of this modal analysis calculation. So I don't start the 2D plots, but the report in general. And if I make it a bit bigger, you can see here the summary, which we already have seen in the settings of the 3D viewer. We have the eigenfrequency values there. Then we can see the characteristic frequencies for the different pairs. Then we have the mass and moment of inertia for the shafts and for the gears. And then the calculated meshing or the used meshing stiffnesses from the ISO, as you see. And if you calculate the bearings with the inner geometry method, you will see the stiffness matrix for the bearings in operation point here for every bearing, which is used in the calculation. And at the end, you have some information about the modal energies, which means if you have the different modes, the bending, axial, and torsional modes in one eigenfrequency, you can check which one is more stronger than the other. So it's a non-unit value, just to distinguish which mode is stronger than the other one. Okay, so this is again the general report for this model analysis calculation. As I mentioned before in the beginning of this topic, we have the force response and also the generation of the Campbell diagram. These two are in the beta state, these two functionalities, and we have already some explanation in we did already some explanation during another web demo about where we just showed 1 hour the system eigenfrequencies or calculation for which was shown from Mr. Zotos. Yeah. So you can check there our YouTube channel to get more information about these as well, but they are still for free. So the force response and the Campbell diagram functionalities are for free. Good. Again, if you have questions related to this topic, you can already write them now or also for sure later. Mr. Stangl is answering a lot of questions at the moment next to me. He's very busy, so just keep him still busy still, please. So next topic is the reliability calculation, system reliability in KISSsys, which I would like to do also directly in this model without changing the model. So if I have this the same gearbox, and I would like to perform or check the system reliability, there is a new icon here on the top in between of the different calculation icons. And if you just have to click on calculate reliability button, and if you like, you can define the range for the service life from minimum to maximum for the plots, or this is also created automatically from the range which makes sense from the software for in order to get the range which makes sense. And here let's use a logarithmus graph for the plots, and I would like to see the reliability of the toothing of the gears, the bearings, and of bearing and toothing subsystem as a subsystem, and also the failure probability of the system. So reliability of the system is by default active, and you can also additionally activate the failure probability of the system. So let's say OK. And KISSsys is calculating now the reliability. Maybe short comment, this reliability calculation is according to a theory from Professor Bertsche, who is from Stuttgart, Germany. And the idea here is that we convert, especially for the gears, is very important that we convert the safeties in lifetimes as hours using a Weibull distribution. For the bearings, we already have some lifetime information from the standard, but the main problem here is the failure probability of the different components in our system. So, for example, for bearings, we have 10% failure probability according to the standard, and for the gears, this is around 1%. So, to make a graph, to make a plot that we can compare all elements, we need to do some mathematics, and there we use a Weibull distribution for that. And these Weibull parameters you can also adapt on KISSsoft side. This I would like to show you then at the end of the demonstration. So first of all, here in this model, we calculated the different plots. We generated different plots which we just marked before. So I have the system reliability. I would like to put them all on top of each other that I can go step by step. So if I go to the system reliability first, and I open maybe here the legend. So what I can see here is I have 100% reliability for the first, maybe 3 hours, 2-3 hours. And then it drops down for the bearing. So we have here the bearing subsystem, which is dotted line, which is this line here, dotted as cyan color here, and the gears, they seem to be okay in the beginning, so up to around 4 to 5 hours, but then it drops very fast down, and so this is the dashed dark green line are the gears, and we can really see nicely that already after 5 or 6 hours or less, we have just 50% reliability left. So it means it seems that first the bearing is the most critical, but if I run longer, if I run the gearbox longer, the bearing it keeps still at 90%, but the gear is really going down very fast to 50% reliability. So, and then now the idea is to see which element, which gear or which bearing is really limiting my life. For this, I go to the different specific graphs. So let's say here, so it seems to be in this range. So this is the total system. Actually, the dotted is the bearing subsystem, and which bearing it is, I can check the closest one, which is the gray, the light gray, it's B1. So for B1, I already get, yeah, here I reach at least at 50 hours or 20 or 30 hours, I reach here 50% reliability. But if I check the gears, this is much worse than the bearings, but this is also the first information which I get from the system reliability, that I see, okay, gear subsystem, okay, and is in this range, and which gear is creating the first, which gear is failing first will be G1, which is dark blue here, the continuous line, and this is exactly the same information what I could see from the system reliability, that yeah, after 5 hours I already reach 5 or 6 hours I already reached 50% reliability. So it means that my gear G2 on SA is limiting my life first, and the second one seems to be either this gear, so is the bending failure of G2 on S2, or the bearing B1. So these three elements I have to check more, and maybe I have to do some changes. I have to see how maybe I have to replace my bearing, or I have to change the design of the gear to reach higher lifetime there. So this was more the graphical interpretation from the plots of these results. We have the system summary as well in the tables here. So you can see 90% we will reach for sure 5 hours, but then it drops very fast because of this gear. So for this speed number 2, I can run 5 hours with this design. Other tables here, we have the system reliability data. It's very interesting, where you can see actually the same information which we could see in the graphs, in the 2D plots, you can also see in the table. And here it's important that you see the lifetime is going from 1.8 hours and it's increasing. And you can check which element is first having where the reliability is different than 1, and then dropping down, going down up to 60 or 50%. So first it seems to be B1, but it keeps very long at 99%. So it's not really critical in the beginning. The same for the bearing subsystem, as you see. But if I go down, if I increase the lifetime, so I see that here this element, which is my gear G2, as we could see in the graph, starts, and it drops very fast. After 5 hours, 6 hours, I just have 67% reliability left, where my bearing is still at 94%. So it's the same information, just in a table format. Yeah. So what we can see here exactly is this gear. For this gearbox, yeah, if you want to have 80%, you just run you can just run 5.5 hours, for example. If you run longer, it drops very fast down with the reliability. So that's it actually regarding the calculation and regarding the results. I mentioned the viable parameters when I explained the functionality. These viable parameters can be checked in KISSsoft as well in the gear calculation under the module specific settings. Here we have a new tab, reliability, and here they can be adapted here. At the moment this was not in, so that's why it was -1. And for the shafts it's the same actually. Here in the module specific settings reliability, here you can see the viable shape parameters. Again, they can be adapted accordingly if you want to use different one from the which is proposed from our software. Okay, so again, if you have questions to this topic, to this functionality, just feel free to ask. Yeah, Mr. Stangl is ready and yeah, would like to help you there as well. So now we reach already the handling topics. So we did the system calculations, we already finished to show. So now I go further to the handling, which is first I would like to show you first maybe the power split kinematics. So let me open one of the models which I prepared. No, this one. So power split model, which is the basic power split model, which shows such a standard or characteristic kinematics where you have one input shaft or input gear, which is meshing with two gears, and then it comes again together to one gear. So this is just a representation of such a system. For sure, what happens here in between can be much more complex in reality, but this is just to show you the principle here. If I activate the 2D view now, if I run the kinematics in this way, it's not possible. For sure, we will get the error because it's not clear how we distribute the load between the two to the different paths, the power paths. So up to now, you had to create or manipulate the kinematic calculation function by creating own defined functions in ClassCAD, and then it was difficult to adapt if you did some changes later and so on. So all these steps are not necessary anymore. We made it much more simplified. If you go to system, we have a new function there which is called define power split. This is just an information that in some of the complex models it may not work already, but we are happy if you can send also the most complex models to us, where you have power splits, to extend our functionality here. Okay, and then I say, okay, I have 50% distribution from the left to the right side. So here we can see that the kinematics can be calculated automatically, and I could also check the different load values. So GP1A is this path, GP1B is this path, and here F1 is the torque on the first gear, F2 is torque on the second gear. The same here, F1 torque on the first gear, F2 is torque on the second gear, and we see that they are the same for both paths. So this is one one of the different models, one of these cases where you need this power split functionality, which is now much more simplified. And I have also another model which is a bit more complex, just to show you that it doesn't just work for cases where you have one gear meshing with two gears. It's also working if you have one direct pass, like this model here, and then a split again. So now for this model, the system actually, yeah, did it a bit fast, I think. I was too fast with the 2D viewer there. Okay, let's start it again. So, okay, so let's start 2D viewer. Yeah, so it's not just here the basic split where you have one gear meshing with two gears. It's also here a direct pass, and we have to define here at least two times. So you have to define this split here between these two paths, and then here internally again this split here. And this is also working here in this model. If I go to define power split, and this is for the first split here between this and this pass, let's say 50%, and here I use 20% of the total load here and 25% here for the other two remaining paths. Okay. And then it can be calculated. I could also use different proportions of the loads in different paths. This is just to show you that in different situations can be really helpful now, this new functionality. Okay, next point is the settings table, actually. And for this, I would like to open one of the prepared models, simple two-stage helical gearbox. Okay. And here I would like to add the settings table from the element box. You can find the settings table. I will explain you shortly what it is. This settings table can be really helpful if you want to make some global, if you want to define the global settings in a system, like for example the lubrication settings, the lubricant temperature, or you want to define the material for every element in your gearbox, for the gears, for the shafts. Here directly the system required lifetime calculation methods at one place, the temperature settings on the shafts, bearing friction, and some additional required root or flank safety for the gears if they are not depending on size, and so on. So this is our definition, how we create this table, but it's also new now. It's also possible to extend this table, or you could also delete some lines or extend this table. Just what you have to do, what you have to know is that you have here a variable which is already existing in one of these calculations, or in all of these calculations. It depends on where you want to control it. So let's check here. Let's make it again to English. So if you go to properties window, this calculation, you have different variables, and there is an ambient temperature variable amp temp, which is nowhere controlled here in the settings table, but now what we could do, we have this variable also in this gear pair. So in every gear pair we have this variable, and we would like to control it globally. What you can do now is just go to Settings table, right mouse click, and here add the variable, and variable name is amp temp actually, like in a gear pair, and the table entry name is the name here on the left hand side, can be ambient temperature. Okay, and we can see that it's automatically added as a additional line here in the table. So if we check this variable, it's now disconnected. So if I say, okay, I would like to have 30 degrees and I would like to connect this variable for all existing variables, for all existing elements in my model, and then I can go here and check it's automatically set through this expression, and it's set to 30 degrees. The same also for the second calculation. So in this way you can extend as you like your settings table. Okay, then the last point regarding the handling improvements. Most of you maybe never used it. We have also the option to create 2D plots in KISSsys, and one of the let's say one of the best examples there, or where it can be really helpful, is if you did the efficiency calculation and you did maybe a temperature spectrum, you calculated temperature spectrum, so the temperature change of the oil in your gearbox over the time here, and you would like to plot this in a 2D plot. For sure, this is possible to do in Excel, but the motivation here is why it's interesting, or it's nice to do it in KISSsys, is that you can have the information already here in the same interface, and if you would change the values, it will automatically update in KISSsys. So I would like to show you just how this can be done. If we go, so normally you don't have this 2D plot element here in the model. I would like to delete it and add it just from scratch from the element box here. You can find the icon, the element here next to the 3D viewer, because it's 2D plot. Close it. And first of all, I have to know where these variables are saved. And if I do the temperature spectrum calculation, I can find it on the properties window under the variable total temperature here, or total time. So I would like to take the whole variable. I would like to copy it and then go to 2D plot, right mouse click and go to dialog. First of all, you have to do the settings for the plot, which is where you define the title of the x-axis, which is in our case the time in hours actually. And the y-axis would be the temperature. Which is in, let's say, in Celsius. We have the option between a logarithmic plot logarithmic axis for the x and logarithmic axis for the linear, or logarithmic axis for the y-axis. Let's say use linear. You can also have multiple curves. Just want to show you how you create one. And then for the x data, this is our time actually. So I don't use the total temperature. I use the total time variable here, which is this array. And here for the y data, I use the total temperature data. And the title is maybe oil temperature over time, for example. That's the title of my graph. Now, let's make it maybe capital. So, and the color, I would like to have it red of my line. It's also here maybe one comment for the x and y data. It's also possible to enter directly the numbers with commas. or you can also read a file in here, which can be a CSV file or a text file. Let's say OK. And then finally, what I get is such a graph, which shows me the change of the oil of the oil temperature over the time here, starting from 31.9 degrees and going up to 44.8 degrees. Yeah. So, and the nice thing here is, the motivation here is, if I get different results, if I do a different calculation, if I run it again, if I update the plot again, I would see the change directly here, yeah, which can be used for documentation purposes then in the next step. Okay, so if you have also questions to the handling points, feel free to write questions. And now we check the questions which you sent to us. Yeah. So let me see. Okay, there is actually there we didn't get too many questions, I think, in general. Yeah, if you have more deep questions, you can just send them directly after the web demo, also by email, either to support@kisssoft.ag or info@kisssoft.ag. So if there would be some interesting questions, I would read them loud, but there is at the moment nothing really which we can mention for all. So then I hope this was interesting, that you could see once in 1 hour all the different features, or the interesting features in a new release of KISSsys. Yeah, we do it. This is the first time when we did where we did it for 1 hour, just KISSsys without KISSsoft, because we had quite a lot of things to show. And yeah, I would like to thank you very much for attending to the web demo. And as I mentioned, the additional questions you can write an email for the additional questions, and we will for sure have additional web demos for KISSsys in future. So please keep checking our website, and not to forget that there will take place a KISSsys basic training, or a KISSsys general training here in Rubicon on the 18th of September this year. So more information about the schedule can be found on our homepage, or in the handout, which you can download as a PDF from the webinar tool. And yes, I wish all of you a nice day or evening, depending where you are. Depends always on the time region. And yeah, hope to meet you next time. So bye, have a nice day, or have a nice evening.